Hello my people, hope we're doing well. In the last video we sort of introduce sequences in series again, introduced sigma notation, showed you sort of what it means in terms of representing a series, representing a sum. And then we ended with the summation formulas. In this video we're going to actually put those summation formulas to work a little bit. But we need to basically talk about two properties of sigma notation, and in this way they're kind of similar to limits and derivatives and stuff like that, which shouldn't surprise us. Just like limits and just like derivatives, basically the coefficient can come along for the ride, meaning that you can actually pull it out. And when you pull it out and it fails to be a piece of the argument of the sigma notation, really what that amounts to is basically a GCF, okay? But you need to recognize the fact that you can pull out, because basically if you were to basically list out all of this, this would wind up being C times a sub 1 plus a sub 2 plus a sub 3 plus dot 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 all the way to a sub n. And over here, this would have just been C times a sub 1 plus C times a sub 2 plus C times a sub 3 plus dot 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 plus C times a sub n. And you notice that the only difference between this and this is basically just factoring it out, okay? This winds up being an expression of the commutative property, meaning that just like with limits and derivatives, the limit of a sum or difference is the sum or difference of the limits. Here, the sigma notation of a sum or a difference winds up being the sum or difference of two sigmas, and really what that means is it just winds up amounting to the commutative property, right? Just a rearrangement of the terms. So you need to know that one too. So for those two, what we're going to do is we're going to use these two principles to take the two that we're familiar with, the two examples we had in the last video, and pull them apart so that we can use the summation formulas. So this is going to become 2 times sigma I is equal to 1 to 8 of I minus sigma I is equal to 1 to 8 of 1. And once we've done that, we know basically that this has a sigma notation, a summation formula, right? And that summation formula was the first one that I asked you to memorize. It's this one, okay? So we need to use the n times n plus 1 over 2. So basically our n in this particular case is 8. The 2 of course coming along for the ride. n plus 1 over 2. Now this one doesn't really need a formula. I mean, you can memorize it as a formula, but basically what this means is 1 added to itself 8 times. And that's just simple multiplication. Okay? This right here is 72. Of course, the 2's cancel out, and you get 72 minus 8, or oh my gosh, that's 64. That is exactly what we got when we did it sort of longhand. Okay? This right here can be split apart. I is equal to 1 to 6 of 3. Again, we don't need a formula for that. That's 3 added to itself 6 times. That's simple multiplication. And here, this is going to be I from 1 to 6 of I squared. Now, what that means is I squared added to itself 6 times. So 1 plus 4 plus 9 plus 16 plus 25 plus 36. But let's go ahead and use our formulas. So we know that this is 6 times 3 for that first term. This second term, I'm going to use the formula, and that formula is the second one that I've asked you to memorize. Those two factors ought to be familiar, and then it's basically that third factor winds up being the sum of those two factors, and then divided by 6. Okay? So what I have here is, here's my n value. My n value here is 6. It's going to be 6 times 7 times 13, all of that over 6. Well, that's going to cancel out pretty easily, and that's going to wind up being 18 minus 7 times 3. That's 91. And so if you have 18 minus 91, guess what? That's negative 73, and that confirms what we saw by formula, that confirms by formula what we saw longhand in the previous video. Okay. So make sure you have the formulas out in front of you. I'm not going to be consistently reaching for that formula sheet, but I wanted to do it on these first two familiar examples from the last video before we moved on. All right, and over the next couple of pages, I have used different variables. On this page, I'm using I. On the next page, I'm going to use N. And on the following page, I'm going to use K. It really doesn't matter, but I want you to sort of be comfortable and familiar with all three variables because all three are going to be used. Now, there's certain times that we use particular variables, and you'll sort of get the hang of that as we move along. Now, this one right here, again, two terms, again, needs to be split apart. And we have I is equal to 1 to 10. The 3 comes out. We want to just leave the I in terms of the sigma notation. And then I is equal to 1 to 10 of just 1. Now the formula for I is n plus 1 over 2. Okay? And that winds, our n is 10. Our n plus 1 is 11 over 2. And so what that amounts to right there is basically 55. So 55 times 3, right, which is 165 plus 10, and I'm going to get 175. And if you're thinking to yourself, surely not, well, let's go ahead and check our answer, right? And we have the sum from in 1 to 10. Like I said, the choice of variable is arbitrary, so the fact that on the calculator screen it's in instead of I, not really an issue. 175. Alrighty, let's move on to the next one. Okay, now what happens here is we simply again need to break it apart using the two properties that we had on the previous page. And we recognize the fact that our in value here for our formulas is 8. Now the first one, I don't need a formula. It's 2 added to itself 8 times. That's 16, right? And then the 3 comes along for the ride, and my I squared formula is n times n plus 1 times 2n plus 1 over 6. So n is 8, n plus 1 is 9, and 2n plus 1 is 17 over 6. Now, if I actually multiply all of that out, right, that 3 inside the 6 can cancel with this 3, the 2 inside the 6 can cancel with the 2 inside of the 8, and so really that's 4 times 9 times 17. But I will go ahead and save you the suspense. The sum is negative 596. And if you're thinking to yourself, really? Well, let's go ahead and check it. So we're going to go to that scroll up menu, press 2 for the summation. N is 1 to 8 of 2 minus 3 n squared, and we get negative 596. Cool, huh? Alrighty, let's do a couple more examples. Actually, we're going to do 4 more examples before we move on to a little tweak of what we're doing here. And in this one, it's the first 40 terms of n squared minus n. We don't have any coefficients to pull out, and that's actually, you know, that's not a huge deal, right? And so we're going to get 1 to 40 of n squared, and then 1 to 40 of n. So what's going to happen here is the n squared is going to be 40, 41 times 81 all over 6, and this is going to be 40 times 41, all of that over 2. Now this is going to be a rather large number. It actually winds up being 22,140 because the squares do get up there pretty quickly, right? This one, however, the 2 cancels with the 2 inside of the 40. That winds up being 20 times 41, which is 820, and you wind up getting 21,320. And if you want to check it with your calculator, you're more than welcome to do so. I'm not going to check all of these with the calculator. In this one, again, we're just going to pull it apart as we know how to do. Okay, now this one again doesn't need a formula. I know that that's 1 added to itself 20 times, so it's just 20. This one, however, I see this up here. That's going to be the number that goes into my formula, And since it's n cubed, we're going to get 20 squared times 21 squared over 4 minus 20. And, you know, if you do all the calculations and you work it out, it actually winds up being 44,080. Okay. Now, you might be thinking to yourself, well, if I'm going to use my calculator anyway for these larger numbers, then why do I need to know these formulas? Well, just cool your jets. We're gonna see here in just a little while. You will need the sigma formulas before long, and it won't be something that you can actually plug into your calculator. But of course, we want to deal with them numerically before we deal with what I referred to in the last video as an indefinite sum, right? Where we don't know whether it's going to be, we don't know the number of terms that we're adding up. We're actually adding up, you know, in terms or whatever, okay? But again, like I said, we want to deal with these numerically and become conversant and familiar with these formulas so that they are not a surprise to us, so that they are not the limiting factor when it comes to us working with sigma notation for the sake of evaluating Riemann sums or even expressing Riemann sums. So this one, again, we're going to break it apart. And this sheet, like I said, I'm using K instead of N or I. It does not really matter as long as you're consistent. Okay. Now, this one right here has, it's basically to the first power. My N value is 10, and therefore this is going to be 10 times 11 over 2. Again, that's 55. We've seen that before. The 1.5 comes along for the ride. The k squared is 10 times 11 times 21 over 6. That winds up being 55. Now, if it was just this without the 1/2, the 6 would actually fully cancel because it would cancel with the 2 inside the 10 and the 3 inside the 21. But you're actually going to wind up getting a fraction here because you're going to have this extra 2 in the denominator out here. And you have 385 over 2, which adds up to, not simplifies, to 495 over 2, which is 247.5. So either one of those will be sufficient, or both. All right, and this next one, the only thing that needs to happen here in order to actually execute it, before you pull it apart, you need to see that you need to basically, if only in your head, recognize the fact that that's k minus k cubed once you distribute that k. And so sigma 1 to 15 of k minus sigma 1 to 15 of k cubed, and that's going to be 15 times 16 over 2, and that's going to be 15 squared times 16 squared over 4. Now you could do a whole lot of cancellation. Obviously 4 will get rid of part of one of those 16s, but it doesn't really matter. You're probably going to plug it into your calculator anyway, and you're going to get 120 because this is going to be 15 times 8. And this right here is going to be a little bit more difficult to do by hand, although you certainly could. And you're going to get negative 14,280. All right. Now, remember when I said that basically those formulas only work when you have the interval starting at 1. So we need to talk about what happens when it's not 1, right? So, like I said, the sigma notation formulae only work when the interval of inputs begins at 1. That means that sometimes you need to adjust your sigma notation in order to be able to use the formulas. Sorry, I haven't really been completely consistent as to how to pluralize formula, but, you know, sorry about that. You'll get over it. For example, given the following series, there are several ways of constructing the sigma notation for the sum. So if I have 3 plus 8 plus 13 plus 18 plus 23, that's going to be a really easy one. It's starting with 3, and it's every 5 after that. So it's going to be 5i minus 2, right? If I go from 1 to 6, there are 6 terms. But I don't advise doing this, but this will give you the same exact sum, okay? Because when I plug in 1, the I minus 1 is going to be 0. Just like when I plug in 3, the I minus 3 is going to be 0. So it's almost like I minus 3 instead of I minus 1 compensates for the fact that the interval here goes from 3 to 8 instead of 1 to 6. And if I want to be absolutely ridiculous about it, I can run it from 15 to 20, and instead of I minus 1 or I minus 3, I could do I minus 15. So that gives you a clue as to how to sort of adjust things when it's needed when you're given something like what we see on the following page, which is this. Okay, because you need to adjust it so that when you're plugging it in, you still get the same numbers, but that you actually can accommodate. Now, you could actually do this as I is equal to 1 to 11 of I cubed minus 1 minus I is equal to 1 to 1 of I cubed minus 1. And so basically you basically do it by a subtraction. Now, of course, from 1 to 1, that makes no sense. But if it started at 5, right, you would go I to 1 to 4 in order to evacuate it. But what I want to actually train you to do instead is this goes from 2 to 11. That is the same span as 1 to 10, right? It's the same span because it's the same difference. 11 minus 2 is 9. 10 minus 1 is 9 as well. So what should be cubed here instead of I? Well, you're putting in a number that is 1 less than, like 1 to the left on the number line. So you need to alter the expression to be 1 larger. And actually this winds up simplifying rather easily if you know how to expand a cubic, and you get I cubed plus 3I squared plus 3I plus 1. Well, the plus 1 is going to cancel with this minus 1, and that right there is the equivalent sigma. And I'll show you by calculator here in just a second, confirm it for you. You can do it on your own as well. Now I can pull it apart, and I is equal to 1 to 10 of I cubed plus 3 sigma I is equal to 1 to 10 of I squared plus 3 sigma I is equal to 1 to 10 of I. And now when I use my formulas, I cubed, of course, since 10 is my in value, I'm going to get 10 squared times 11 squared over 4. The 3 in front of that second sigma is going to come along for the ride, and I get 10 times 11 times 21 over 6. And then also that 3 comes along for the ride, and I'm going to get 10 times 11 over 2. Now this first one, if you plug it into your calculator, or I mean, if you want to do it longhand, you're more than welcome to, right? It's going to be 3,025. This one becomes 1,155, and this last one becomes 165, because I think we've seen this before, 55 times 3. That amounts to 4,345. Well, let's go ahead and let's actually look at these, okay? Let's go ahead and just do this original one right here, okay? What we were given. F2, alpha F2, will go in 1, or it actually starts at 2 to 11, and it's going to be n cubed minus 1, okay? Double check that I got it right, that I plugged it in right. 4,345. Okay. Well, let's go ahead and do it like this. Now, n is equal to 1 to 10. And let's do it this way, right here, okay? And you go n plus 1 raised to the third minus 1, right? And so it looks like I've done it correctly, okay? And just for the sake of, giggles, let's go ahead and do it 1 to 10. And it should be the same as that one, which represents this one right here. Boom. All 4,345. Now, like I said, I could have done it this way. And what I would get there is, n from 1 to 11 of n cubed minus 1 minus, and I'm going to put the sigma there even though I don't have to, since it's one term, just to illustrate a point. So I could have done it just by subtraction, and there you go. Okay. Now, let's go ahead and do one more example of this, okay, and then that will bring us to the end of our Sigma Notation review, or sequences and series and Sigma Notation review, and you can go ahead and get started on the homework, and I'll try and, of course, iron out any misunderstandings or any problems next time we come together. Alrighty, this goes from 7 to 23. The difference is 16. So obviously the goal is to conform it to 1 to 17. I'm going to go ahead and pull the 1/2 out in front and just worry about how to transform k. If k in the first term is used to being 7 and now I want to plug in 1, then I'm going to need k plus 6 to be squared instead. Which means that once I actually multiply this out and then start pulling out terms, let's go ahead and just do it this way. That's a perfect square trinomial, pretty easy. So k is equal to 1 to 17 of k squared. On the second one, you can pull the 12 out. It combines with that 1/2. Remember, that 1/2 will apply to all three of these once you actually pull them apart into separate sigmas. So it's basically distribution, and you're going to need to be careful about that. And then, of course, 1/2 is going to be combined with the 36 to be 18. And I don't really care whether you put that in here, which I'm going to, or out here and put a 1 there. It amounts to the same thing. So you get 1/2. 17 times 18 times 35 over 6 is the formula for squared, right? The formula for just the first degree is going to be 17 times 18 over 2. And then the last one is going to be 18 added by itself 17 times. This is going to wind up being 1785 over 2 right here. This is going to wind up being 918, and the last one is going to be 306. You wind up getting 42,033 over 2, or 2,116.5. So either one of these will do. This one obviously is better at communicating the actual value, right, than that improper fraction. Although, like I've said before, improper fractions do have a use. Okay. So we've got a little bit of sigma notation under our belts. We're going to now apply that knowledge to Riemann sums, because Riemann sums with uniform width of subdivisions wind up conforming to a pattern and therefore can be modeled. So first, this is going to aid us from some of the more cumbersome sums that we've had calculated. And second, the formulaic nature of the sigma notation and its summation formulas will allow us to apply a limit and transform the approximate area into the actual area. And as I've said before, that is the ultimate goal. So if you have any questions, as always, please do email me. I will see you in future videos. Bye.